welcome to another edition of Molecular Mania. I'm Amelia.
And I'm Chris.
And today we're going to be talking to you about fluorescence. Fluorescence is a type of light, and light is a kind of energy. And you know this because you've seen plants, they perform photosynthesis, so they get all of their energy from the sun. Now, Chris, what else do you know about light?
Well, there's a lot to it. Light, as you mentioned, is a form of energy, and light travels in packets called photons. So photons can be described by their size, so we use the term wavelength, and they can also be described by the amount of energy they have. So some forms of light have lots of energy, and those forms of light have shorter wavelengths. So an example of that would be ultraviolet light, which, you know where we can find ultraviolet light?
From the sun. That's why all the sunscreens say protect from UVA and UVB.
Exactly, because the amount of energy they have is actually enough to be damaging to the cells in your body, which is what sunburn.
They can screw up the DNA, can't they?
They can do that too. But the first notice that you'd get is the nice red sunburn. Once you see that, then yes, you could damage your DNA as well. So it's very important to wear sunscreen to protect you from high energy light. Now, there's also light that has less energy, longer wavelengths, and that would be, an example of that would be infrared light. So when you've been to a buffet, have you seen the lights that are above the food?
Yeah, they're red and super hot.
Exactly. Those are forms of infrared light. When you have light of longer wavelength, that's usually emitted as, you see that as heat. So we use those lights in order to keep things warm. You might also find it for a reptile light that would emit infrared light in order to keep them warm. Now, in between the two, you have light that has a wavelength between about 400 nanometers and about 800 nanometers. That's the visible light spectrum, which is what we're able to see with our eyes. So, depending on the color of the light, we can use the wavelength. The wavelength dictates the color a little bit. So, have you seen the rainbow, or have you seen a rainbow?
I have.
And have you? What do you see in it? Like what colors?
Well, I see red, orange, yellow, green, blue, and violet.
You think there's a reason that they're in that order?
Maybe the wavelengths.
Yes, exactly. So the rainbow is formed when you have the white light coming from the sun, which when you add all the colors of light together, you get white. Black is the absence of light. So it would be if you have no light coming through, no wavelengths of light. But when you separate them, so the white light from the sun travels through prisms in the atmosphere, like water droplets from humidity or rain, then those prisms separate the light. And the red light, because there's a different energy, it refracts differently than maybe the violet light. And because of that, it's going to move at different speeds, which causes it to separate, which is why we see the rainbow as a separated spectrum of the light there. Now, let's talk a little bit about how the light is formed. So we've talked a lot about color and the properties. Well, the light comes from molecules, and all molecules are made up of atoms, and atoms contain electrons. Electrons give rise to a lot of unique properties of the molecules and atoms, and one of them is light. So under normal circumstances, an atom is going to exist in the ground state. The ground state is the lowest energy state that the atom can be. All the electrons have the lowest amount of energy they can. But if you use something like an electric shock or a very high energy light source, you can give the electrons in the atom a lot of energy, and they're going to use that energy to move up to a higher energy orbital, which this is called the excited state. Now, eventually, the excited state is going to want to relax back down to the ground state because the universe favors being in the ground state. When they relax down, there's two ways that they can do this. You either emit the light, or you emit the energy thermally, or you emit it as light. And
when that happens, isn't that called luminescence?
It is. Luminescence is the term for emission of light, and there's multiple different forms of luminescence. Shall we look at a couple of examples?
I'd love to.
Okay, so for that, we'll go ahead and dim the lights, and we can show you what's on our table.
So here we have a black light. You might have seen one of these at a skating rink or playing laser tag or somewhere else with special effects. It's emitting radiation as UV light at 365 nanometers. And as Chris was telling us, this light excites the electrons in this powder, and when they relax back down to the ground state, they emit photons that you see as this beautiful green color.
So you mentioned radiation. Is this going to hurt me?
Of course not. All forms of light are just radiation. In fact, you're radiating right now. You're radiating heat. Radiate just means to give off.
Got it. Okay. Well, do you want to look at a few more examples?
Sure.
Okay, let's go ahead and dim the lights down, and we'll take a look at a few more examples. Here we have tonic water, which you can see is glowing blue, and that's because tonic water contains quinine, which is a fluorescent molecule, and it emits blue light when excited by ultraviolet radiation. In front of the tonic water, you can see we have these glow-in-the-dark spiders, which one is glowing orange, one is glowing green, and that's because each of them has a different fluorescent dye in them. These are things that you might see around your house. Any sample of tonic water that you have at home would glow in the dark under a black light because it contains quinine. And depending on what dyes they use when they manufacture the spiders, they might glow in the dark as well. But we can also see some examples of fluorescence from the lab. So here we have some copper crystals, some crystals of a copper complex, which are glowing blue. Here we have a terbium complex, which is emitting green light. And here we have a red sample, which is from a europium complex. And these red and green samples right here are similar to what used to be used in CRT TVs in order to make the light come out. Now, depending on the efficiency of how well these molecules emit their photons, that determines the brightness that we're able to see. As you can see, some of them differ. Now, we have some other powders. For example, this one's green. We have some blue, and we also have some violet. These powders are also fluorescing, and due to the different properties of them, we see different colors. So let's turn out the lights. And we can see these ones do not glow anymore. These ones do. So there's a difference. These ones are fluorescent, while these ones are phosphorescent. So let's turn the light back on. The fluorescent ones came back. The phosphorescent ones continue. So we'll turn the lights out one more time. And pretty much right away, the fluorescent ones stop glowing, and the phosphorescent ones continue. This is due to different ways that the light is being emitted. So fluorescence happens a lot faster, phosphorescence happens slower, so therefore we're able to see it for a longer period of time.
Where would you see something like that at home?
Well, if you have glow-in-the-dark stars on your wall in your room, they're phosphorescent. That's how they glow. You might have used it in glow-in-the-dark paint, that's phosphorescent because it lasts for a while. And in buildings, if you've seen exit signs that stay lit up after the lights are out, those are also phosphorescent.
So here I'm demonstrating something called triboluminescence. So I'm actually physically breaking the bonds between the molecules, and you can see that light is released when I do this. This is the copper complex, and it's releasing blue light. Here's a europium complex that's releasing red light. And you can actually do this at home. Just get some wintergreen light lifesavers and go in the bathroom and turn out all the lights and look in the mirror as you chomp down really hard, and you might be able to see a flash of light.
This is another example of chemiluminescence. Here, I have a solution that contains luminol, which is an organic molecule, and also contains a copper catalyst. Amelia has a solution of hydrogen peroxide, which, when the two of these are mixed together, you'll get a chemical reaction that's going to cause some of the bonds in the luminol to break, and the energy will be emitted in the form of light. So, shall we take a look?
Sure.
All right, so let's mix. And we'll very slowly do this. Go ahead and pour. So what you see here, the blue color, comes from the luminol itself. This is the light, this is the energy we're seeing from breaking the bonds. Now the blue color has nothing to do with the copper catalyst that is in the solution. But other catalysts can also be used.
So if you've ever seen a show like NCIS or something, they'll spray some luminol and droplets of blood start to appear. That's because the iron in your blood can also be a catalyst.
So the blue color is specifically for the breaking of the bond that we're seeing. And this is chemiluminescence. Now, you also notice that this doesn't last nearly as long as a glow stick. And that's because the way that the light is being emitted is different than that from the glow stick reaction. Here, we're observing the light directly from breaking of a bond, instead of transferring energy between other molecules. And now if we hold it all up, there's the luminol, and this is chemiluminescence. Thank you for watching. We hope you learned something about luminescence.
And please check out our channel to see more videos from Molecular Mania.